Good morning, everybody. My name's James Lawrence, and I'll be presenting this morning the Geomorphology of West Cumbria, a tale of two hypotheses. I will be doing this jointly with Sinead. As was said, I'm a reader in geological engineering at Imperial, and Sinead is a researcher, and really all of this work is Sinead's. We should also just recognise that this work is funded by the EPSRC and also by Nuclear Waste Services. In addition, at Jacobs, Chris Coleman works. Chris Coleman works, and he is Sinead's external supervisor. So just an outline of the presentation this morning. We're going to provide a little bit of context about why this is so important to both infrastructure and hydrogeology by providing a little bit of background on the nuclear industry before we look at the previous work done, because the history, understanding the Quaternary and the geomorphology in the region is absolutely vital. Before then, I hand over to Sinead, who will be focusing on her approach, her methodology, going through the types of landscape, before we look at the mapping, where we combined remote sensing with physical field work, looking at landforms and materials, before finishing off with our interpretation, and then I will sum up with the conclusions. So the UK has a, just a moment, I'm just going to get the laser pointer. So the UK has a mix of electricity and energy sources. These go from our renewables, such as wind and solar, down through gas. But at the bottom here, you will see nuclear. And you can see here for the last 30 years and going back beyond that, nuclear has been a very important part of the UK's energy and electricity mix. And it forms what's called the base load. It's always providing us with constant electricity, unlike, say, for example, renewables, or gas, which we turn up or down depending on demand for electricity. Currently, we have around 15% of our electricity generated by nuclear. However, the government has ambitions to generate a new 24 gigawatts of nuclear energy by 2050. So this will account for around 25% of the UK's electricity needs. So we're talking about West Cumbria, and in the UK has been a nuclear nation since the 1940s. And that was mostly to do with the weapons race initially, but then subsequently, as an offshoot of that, we also became we focused on the commercial nuclear power stations. And the UK was actually had the first commercial nuclear power station, and you can see here what was called Windscale and the Calder Hall works, where the Queen opened the first nuclear power station, and you can see here the golf ball, which was an advanced gas-cooled reactor at Windscale. And so as a result of all of this early nuclear work, and as a result of the weapons program and the power stations, we have a nuclear legacy. And we have a nuclear legacy in waste. And you can see in the bottom picture here, an example of some of that waste that we currently have. And the waste we currently have is stored at surface. And over the last 30, 40 years, we've taken a lot of care in the management of that waste. But in the early days, in the race for weapons, not much consideration was given to the radioactive waste. And so we have, for example, these waste storage ponds, such as these ones at Sellafield, which, if breached, would be a very serious environmental disaster. And you can see clearly that this is rusting. It is open to the elements, so wouldn't meet what we would consider current engineering standards. And we've got quite a lot and a varied mix of waste. And we're going to be focusing on the high-level waste, HLW, which only makes up 0.1 of, or less than 0.1 of the actual inventory, as we call it, how much waste there is. But it accounts for over 80% of the total radioactivity and is generally heat generating. So it's generating a lot of heat, gives off a lot of radioactivity. It's the sort of stuff you don't want to be near or around. Then we've got this 11%, which is intermediate level waste. And these two wastes, the intermediate and the high level waste, are destined to be disposed of in something called a geological disposal facility. That's an unengineered underground facility. And then you've got the low level waste, and that a lot of that is currently disposed of at the low level waste repository near Drigg in West Cumbria. So we're already disposing of that. And this waste is either exists now or is destined to exist when we construct the new nuclear power stations, and there will be a lot of it. 4.5 million tonnes, although, as you can see here, the majority is very low-level waste, and that will just be disposed of in licensed sites. So I mentioned a geological disposal facility. When I was working for RWM, this is what I was planning. And you can see what you've got is, if we take there are several different design concepts, and this is one of the design concepts. And you can see you have a surface facility which will take receipt of the waste, and then a series of drifts and shafts and adits, in this case going offshore, where the waste will be deposited, and you will have that high-level heat-generating waste, and that, because it generates heat, the heat has to disperse, so it's spaced out, whereas the intermediate-level waste can be packed more closely together. So this is one of the design concepts, and what's important about this is it will be probably between 200 and 1,000 metres below surface, and that's important because we need to isolate the waste from the surface to limit the release of radionuclides. So there is a requirement on the engineering of the facility, but eventually that engineering will break down probably after around 10,000 years. And then for the next 100,000 to 1 million years, timescales we're not normally used to dealing with, we will put a requirement on the geology, so it must be stable, it must stop the movement of radionuclides, so we rely on the groundwater to not be moving very fast. And of course, we must be able to construct in it, so we must be able to construct our geological disposal facility. Currently, NWS have a siting process, so Nuclear Waste Services have a siting process where it is a volunteer process, community-led, and they are asking communities to come forward and consider to host a geological disposal facility. One of the communities that has come forward and suggested that is Mid Copeland and South Copeland in West Cumbria. So you already have 2 licensed sites here with Sellafield and the low-level waste repository. So the community has a nuclear history. And the concept is that the waste will go somewhere in this offshore environment up to 22 kilometres offshore. And it would go, the ambition at the moment is it would go in the Mercia mudstone. Now the Mercia mudstone can be seen here in this sort of light brown colour. And this is the coast. And you can see it's very thin at the coast. So they would have to go quite a long way offshore to get the thickness and the depth of geology required. And although the Mercia mudstone has a number of features which would support a GDF, such as it's a competent material. So we've got the strength. Groundwater is probably moving very slow. We also have a number of challenges. The distance we need to go offshore. And you can see a series of faults running through these rocks as well. So, so a number of major challenges as well. But capping the Mercia mudstone, unconformably, we have quaternary deposits. And this shows us the coast here and the thickness of the quaternary in the Irish Sea. And that thickness can be up to 100 metres of quaternary sediments in direct communication with the Mercia mudstone. So potentially understanding these deposits is very important. We have features like the Calderton Channel, which is a tunnel valley carved out by the ice and subsequently infilled with quaternary sediments. There have been a number of glacial landforms identified on the seabed, such as megascale glaciation, ice streams, etc. And as I said, it's in direct contact, unconformably, with the Mercia mudstone. So this hopefully highlights my first point about the importance of understanding the quaternary from an infrastructure perspective. The site investigation alone is intended to be a nationally significant infrastructure project. The construction is going to be a nationally significant infrastructure project. So understanding the quaternary is important to the GDF because for the site, for the safety cases, whether that be environmental, operational, post-closure, and we need those safety cases because we have to demonstrate safety to the Office of to the regulators, the Office of Nuclear Regulation and the EA. In the early days, it will support the siting process, such as where you put your offshore installations for the site investigation. The quaternary needs characterizing. What are its properties? Because any onshore facility will be on it. Any drifts and shafts will go through it. And of course, the quaternary provides us, if we have to keep this waste safe for 100,000 years, it provides us insights of past climate and therefore future climate scenarios. And as I said, it's in contact with the Mercia mudstone. Secondly, and very importantly, we have the low-level waste repository at Drigg. So Sellafield's here on the West Cumbrian coast, here's Drigg. This site's been open for decades, since 1959, and has been in receipt of low-level waste. The actual site dates back to World War II, where it was a Royal Ordnance factory. And until the late 80s, early 1990s, the waste was disposed of in clay-lined trenches. However, since then, there have been a series of vaults constructed. So you can see the trenches here that have now been capped. And then you have these vaults, 8 and 9 here. And you can see 8 is almost filled, and the waste is put in shipping containers, and then they are stacked in these engineered concrete reinforced vaults. And you can see 8 is almost filled in this figure, and then 9 currently in receipt of containers. So why is this important? Why is understanding the quaternary important for this infrastructure? Well, it all feeds into the environmental safety case, which is needed to demonstrate to the regulator, the EA in this case, that it is safe to continue to dispose of low-level waste at Drigg. This is an example of the 2011 environmental safety case, and it's made up of a series of reports, including a hydrogeology report of the site, but also the wider region. And this is applied research, so our work has been feeding into the next environmental safety case, which is due in 2026. And just to say, the last one in 2011 identified that tritium, probably from the Drigg LLWR site, had escaped and was found in this channel and subsequently found in this SSSI. And the distance from the edge of the site to the coast is only around 350 meters. So moving on to the second part, we're going to look at the previous work done. So we will focus on what NIREX did in the 80s and 90s, and then we will focus on Merritt and Orton's work, their their seminal paper in 2000, before looking at that environmental safety case in 2011, and then the Frugro and Jacobs work from 2016 to which culminated in a paper by Coleman et al., and then the work we have done at Imperial subsequently since 2020. But just to provide a little bit of background and context, we will be focusing on a series of late Devensian glacial events. The last glacial maximum, which was a period of maximum ice during the Devensian, the Goth Force Oscillation, which was the first ice re-advance after the LGM, the Scottish re-advance, which was the final re-advance before deglaciation. Then we had deglaciation, and then we had this, this cold snap known as the Younger Dryas before the Holocene today. So NIREX were an organisation set up in the 80s by the government and have continued to this day in various forms. Today you would know them as NWS, Nuclear Waste Services. And they were the government organisation set up to investigate West Cumbria in the 80s and 90s for a geological disposal facility. It's worth saying this was just for intermediate level waste, so that's that non-heat generating material. They undertook a series of deep boreholes and investigations in the early and mid-90s, and they also undertook a series of quaternary boreholes. They did 25 quaternary boreholes that you can see here. So again, we've got Sellafield and we've got Drigg here, and you can see these boreholes in red. And they looked at other data. So in yellow, we've got 3 boreholes that were from BNFL, British Nuclear Fuels Limited, that had been previously drilled. From this, a series of transects or cross sections were developed. However, there were a number of issues. This is a glacial environment, and you can see here that the boreholes, so it's very heterogeneous, and you can see here that there was considerable space, over 1 kilometre, between some of these boreholes. So when you're correlating those kinds of distances in very heterogeneous glacial environments, there's maybe a great deal of uncertainty in those correlations. So a certain amount of uncertainty in the correlations between the boreholes. They also looked at coastal sections, and this is the area we're going to be focusing on. So you will see a lot of the maps go from St. Bees up here, down to Ravenglass in the south, and in between you've got Sellafield and the LLWR, and we're going to focus on 2 sections, Seascale and Drigg, and these are quite important, the coastal sections there. Merritt and Orton, then in their published work in 2000 and the NIREX reports that they did in the 90s, they identified the Drigg cliff section as having the Drigg beach till at the base, moving up through some glacial fluvial deposits, then into the Fishgarth wood till, and then more glacial fluvials. They also looked at the Seascale cliffs, where they had the Ravenglass till and the Howe Man till. Now, what's important about these is, if we look at this Drigg beach till, this was considered to be from the Gosforth Oscillation, and the Fishgarth till was from the Scottish re-advance, and you can see that at least the Drigg beach till is absent in the NIREX cliff section, because the Ravenglass till is actually the oldest of all these in the LGM. Merritt and Orton then developed a lithostratigraphic framework from their findings, which they published in 2000. They divided this into 3 provinces: the West Cumbrian Drift Group, which was made up of 6 formations, and this had its origins in what is called the Irish Sea Ice Stream, with the rather unfortunate acronym ISIS. The Central Cumbrian Drift Group, which again were glacial sediments, but these weren't from the ISIS, these were from the Lake District glaciers, and then the Solway Firth Group, which were non-glacial sediments. So please just note those. And they came up with a paleo-environmental reconstruction. We had the LGM, last glacial maximum, where you can see here, so we've got the coastline in black, St. Bees there, Sellafield, Drigg, and you can see the ISIS coming, you can see there's no exposed land. So you have the ISIS coming down here, and then the Lake District glaciers being drawn down. As we move towards the end of the LGM, you can see the ISIS is very near the coast in present day, and the glaciers have, the Lake District glaciers have receded up into the valleys. And you can see you're having a series of deposits in the form of outwash plains, deltas, and Sellafield and Drigg are exposed, no ice. Then we have the Gosforth Oscillation, where the ISIS advances onto the coastal plain. The Lake District glaciers come back down the valleys, advance towards to Drigg, and you have outwash plains and delta fans just around Drigg, and Drigg potentially covered in ice. Then you have the Scottish re-advance. This was the final re-advance. Again, you can, and what you can see here is the ISIS coming down the coast and potentially coming on shore and going over Drigg. But the Lake District glaciers are in the valleys. And then we finally have our deglaciation, and then this cold snap in the Younger Dryas, where we can see cirques just forming in the top parts of the valleys. Now, why this was important to the environmental safety case is Merritt and Orton's lithostratigraphic framework was incorporated into this. However, Merritt and Orton, they used an event stratigraphy, whereas in the 2011 environmental safety case for Drigg, and you can see the LLWR Drigg here, they used a lithophases approach. And when they did their hydrogeological modelling for the safety case, they subsequently found out that the approach they had of the water going through the quaternary into the underlying bedrock didn't seem to correlate with observations and measurements. So this is how we come on to the work done by Frugro and Jacobs. And I know you can't see the keys probably very well there, but just focus on the colours. This is Merritt and Orton's work at the top, and then this is Coleman et al.'s publication in 2021. And you can see the tills we have here, the Drigg Beach till and the Fishgarth wood till, but Coleman et al. Had many more, they identified many more layers. And they identified layers of sands and gravels. And the key point here is what Merritt and Orton and Coleman et al. Identified wasn't different. They both identified the same materials. However, what was important was their interpretation. These were interpreted by Merritt and Orton as a series of tills, whereas Coleman et al. Interpreted these as a series of glacial lake sediments. So very different interpretations. Coleman et al. Also had access to LiDAR, and so did LiDAR mapping, and you can see the Drigg site is here. And you can see in the north they identified tills, but towards the south it was a came topography, and the actual Drigg site is on these lake deposits. So that's why we have our tale of two hypotheses. So we have Nyrex and Merritt and Orton in 2000, who identified tills at Drigg and the Seascale cliffs, whereas Coleman identified no tills at the Drigg cliffs or on the LLWR site, and the clay units were interpreted as lake deposits. They identified, Merritt and Orton identified the ISIS overriding the Drigg cliffs and the LLWR during both ice re-advances, the Gosforth Oscillation and the Scottish re-advance. Coleman et al. Suggested that the ISIS did not override the Drigg cliffs or the LLWR, and Merritt and Orton didn't see any evidence of an ice-dammed lake, whereas Coleman et al., they interpreted these sediments as lake deposits and as an ice-dammed lake, with the ISIS coming round to the south of Drigg, and that created the ice dam, which melted, so the lake would have drained and refilled on multiple times. So I'm now going to hand over to Sinead, who will present some of her research.
So hello, I'm Sinead. So now I'm going to talk you through our work and how we've tried to contribute to these two hypotheses. So initially we began working remotely, looking at LiDAR digital elevation models during COVID. So we had 1 meter resolution digital terrain model. We had hillshade, elevation and slope data for that. And so we initially looked at this to identify any landforms in the area, and we had a landform criteria to help us do that, so what we were looking at. I'm combining this with borehole records, so those ones James mentioned, NIREX, but also other ones that were available. So thinking about how these sediments and landforms are linked, so sediment landform assemblages, so groups of recognisable geomorphology in sediments which occur as single or a linked set of processes, so telling us more about that depositional environment. And then once we had our initial map, we did some targeted field mapping, so I spent around 3 months in Cumbria and West Cumbria in total, so if you need any hotel recommendations, you know where to come. So during our field mapping, we did some morphological mapping of these landforms, so thinking about the shape of them, the slope angle, etc., and added this to our map, and also any sedimentological evidence. So we found some inland exposures on these landforms to help us again with that sediment landform assemblage interpretation, and also looking at the coastal cliff sections that James highlighted earlier. So once we did our remote mapping and our field mapping and looked back and forth between the two, we combined it all and did our final landform identification, and that led us to our final map, which you'll see in a few slides' time. So before I go to the big map, the final map of the geomorphology, I'm going to unpick the area a little bit. So these are from figure 3 to 6, so this is from our paper, which is currently in review. So we're going to look at the area here, so figure 3, which is the area between the LLWR and C-scale. We're going to look, going towards the valleys, this area here by Gosforths, look at Lower Wasdale. This area by here, so this is called Holmrook, and this feature here, this is Muncaster Fell. It's a big granitic intrusion of nearly 300 metres tall. And then thinking about the coast, looking at the coastal sections at C-scale, and I will also briefly mention Drigg as well. So figure 3, this area by the LLWR. So this here, this is of the LiDAR I was looking at, and the red box here is where I was standing when I took this photo, and the arrow there, so I was looking north towards Sellafield. So we've got quite a few different glacial landforms in this area and sediments, so I'm just going to go through them and briefly tell you what they are, so for people who are not glacial geomorphologists in the room. So we have moraine ridges, and these are important when we think about reconstructing ice. So they tell us the different extents of the glacier, so we have different types of moraines. So we have terminal moraines, which tell us the maximum extent the ice advanced to. We have lateral moraines, so think about lateral extent of the glacier. Retreat moraines, showing so we can map the retreat of glaciers and so on. And these are typically formed of anything that was in the glacial foreland at the time. So it can be glacial fluvial sediments, so sand and gravel, and also tills. So we also have paleo lakes, so that's fairly self-explanatory, so past lakes, which are now infilled. We have kames, so part of kame and kettle topography. So this is linked with ice stagnation and retreat. So as meltwater is coming off the glacier, it deposits all these glacial fluvial sediments and forms these kames. So these are flat-topped mounds, typically formed of sand and gravel. Sometimes you get till in them. And alongside this, we get kettle holes. So when blocks of ice fall off the ice margin, they form little depressions filled with water, and that's our kettle holes. And then in some paleo landscapes like West Cumbria, these can be now infilled with peat, and you can recognise them by dark patches of vegetation, normally fairly circular. So thinking about what we've seen in this area here, so these orange polygons, these are our moraine ridges. Representing ice margins, so all the geomorphology I'm referring to from my work we're assuming to be from the last ice re-advance, so that Scottish re-advance before deglaciation. So these moraine ridges, they tend to be singular but closely spaced. They can be linear or curved, and they're fairly steep in this area. They have slope angles up to 45 degrees. So that tells us they haven't been overridden since deposition. You'd expect them to be a lot flatter. So we think that the Irish ice stream came down past Sellafield, got to this area, and stopped around here. And it links up to a deposit at Seascale, which you'll see in a couple of slides' time. And at the same time, ice was coming from the Lake District, so Wasdale, coming down here and reaching these moraines here. So the ice was meeting in this area, so thinking possibly ice coalescence. It's mentioned in the literature that it likely happened, but no one's really mapped out exactly where this is, because no one's focused fully on the geomorphology, except briefly when Coleman did a bit of mapping a few years ago. So then we have got meltwater channels here, and these are all around near the moraines and across the region. So these meltwater channels, because their proximity to the moraines, is seeming to be ice marginal. We've got these lakes here. So this lake here, this is now a SSI, it's called Hassan Moor, and it's full of peat. Within the lake, we've got paleo shorelines, so we had changes in lake levels. And the green around here is cane kettle. It's probably in lots of glacial fuel sediments, and we've got these cane mounds here and kelp holes, which would have formed as the ice was retreating away. We've got some cane mounds here close by to the moraine ridges, and potentially might be superimposed onto some other older moraine ridges. So moving away from there, going towards the valleys, so that purple lake there is this one here. So on LiDAR, it's a flat basin with a negative relief. We've got more paleo shorelines in it, so again suggesting change in lake level over time. We have meltwater channels here, draining from representing former drainage from this lake. We've got more glacial fluvial sediments around and cames again, so very much forming during the retreat of that Lake District ice going back, and then lakes forming in front of it as it was retreating. So moving to this area here by Muncaster Fell, we've got a fairly flat plain here with some moraine ridges around the side. So we've got lots of channels in this area, and there's quite a few borehole records, so these purple circles here. And around the surface, the first few metres, these are full of sand and gravel, so glacial fluvial sediments, and also some laminated clays, so likely some small proglacial lakes in that region happened. So as the ice was retreating away, so this is Eskdale here, so as ice come down, it got to the coast here near the Ravenglass estuary, and then retreated away and stopped around here. There had been Wasdale ice here, and as it was retreating, all the meltwater coming off and forming this outwash plain. So going to the coast now, not looking at LiDAR. So here we've got lots of glacial fluvial sediments again, associated with retreat. So in these photos, so photo A, we've got these old channel structures, and they're quite coarse, up to boulder sometimes in size, so a high energy event, possibly proximal to the Irish Sea ice stream margin. So so we had these channels forming, and we've got more further down these coastal sections. Again, very coarse at the bottom here, high energy, but then fining upwards, and we've got some sands in between, so a lower energy event. So many channels, and then also we've got a raised beach here above the channel. So this is obviously not a glacial feature. This is a Holocene feature, so when sea levels rose, this was plastered on there. So here we're thinking Irish ice stream came down, and sort of an outwash plain environment again around this area. Here's an overview of the cliff section. So all those channels I just showed you is in that blue area there, and these are more filled in blues, that's the channels, and that red line there, that's the raised beach. So moving toward the south, going closer to Drigg. So we're not far from Drigg here, about a kilometre and a half away. We think we have tills here. So here, this exposure, this is where James was showing there's the two tills. So there's the Ravenglass till and the Howman till, so an LGMH till and a Scottish Readvanced one. So I've obviously had a look at these sediments here, these tills, and within them there are clasts which have slight striations on them, so deposited by ice scratching those. So agreeing that ice was around here and deposited these tills. So the Irish ice stream came down the Irish Sea, came to here, deposited these tills, and then retreated away, leaving all these channels. So thinking about Drigg, so just a kilometre or so away. So in this red dash box, this is where NIREX were logging, and also Coleman and Virgo and Jacobs, that body of work. So we've got lots of clays and sands. So similar looking units to Drig here, not Drig, C-scale. So we've got these clays here, but the clays here are slightly, they're moderately stiff, and they're more stiff at C-scale. We have less clasts, and we have these laminated sands in between them. And we also see the deposit on the beach floor as well. This blue section here, I've looked at this one, so this has become exposed since they've done some more logging. So in West Cumbria, there's lots of storms which occasionally bring some of that away, so the material away from the cliffs. And here there's less gravels, so less coarse sediment, so a much, so there are obviously glacial sediments there, but a quieter, low energy environment compared to sea scale. So here is our final map of the area. So we mapped approximately 400 landforms. So we've got, just to go over what I was saying, so the Irish ice stream came down over Sellafield, got to around this point, linking up to that, around that till deposit here at sea scale, and hanging around there. We had ice from Wasdale coming down here, forming these moraines here, and potentially coalescing in this region with the Irish sea ice. We had also more ice coming down from Eskdale, reaching here, potentially coalescing here with Wasdale, and then retreating. And then as these ice masses retreated, forming those outwash plains and those Cayman and Kettle topography areas. So just to try and help you imagine what that might have looked like, I've started doing some drawings. So using them, a 3D LiDAR image that I did an arc scene, so I've just drawn, so here's the Irish sea ice coming down, around where those moraines are, ice coming down the valleys and coalescing here. And then during this period, so during this last ice advance, the geomorphology suggests that ice did not override the LWR during the last re-advance, but likely did in other events. And then the ice, we moved forward and it started retreating away, getting all these areas of Cayman Kettle topography and outwash plains forming. And then ice continues to retreat, more retreat landforms being deposited, and then finally skip forward to just before the Holocene. Younger dry ice would have just had these small cirque glaciers in the valleys. So thinking about the contemporary analogues we have now to help us again see what West Cumbria might have looked like, and so just to say we're going to be mapping, we've also been looking at places like Iceland, Greenland to help us with our interpretations, thinking about glacial land systems in that area. So here, this is in Iceland. We've got these valley glaciers coming down, meeting, like you'd imagine in West Cumbria, and forming these dark lines, which are medial moraines. And sometimes lakes form in front of them, sometimes they don't. And you have outwash plains and all these glacial sediments in front and tills and things in the area. And then this is a photo from West Greenland. So we've got an ice stream coming down here, and it's drawing down these valley glaciers and coalescing here. So a bit like in West Cumbria when the Irish ice stream was coming down, drawing down the Lake District glaciers to the coastal plain. Now, trying to go back to engineering geology, I started drawing some conceptual ground models to try and help us think about the types of sediments we have there where we don't have information. So we're trying to think this land system approach, looking at these, look at the geomorphology, and we can make some assumptions about what sediments there might be there. So glacial sediments, highly variable over a short space, they can be, so it can be quite difficult to predict. So that's why it's important for us to look at the geomorphology to help us with those interpretations. So just a simple one so you can read some of the words. So just pointing out, obviously, the infrastructure, the LWR, Sellafield, we've got the railway here close to the coast, and some other things like a quarry, and this area is also popular for tourists in the valleys. And then just trying to combine that with our work, so our geomorphology and our, the geomorphology and our knowledge of the sediments. So now I'm going to hand over back to James to do the conclusion.
Brilliant, thank you, Sinead. Yes, so you saw this slide as I finished off last time, but this time we've added an extra column here, the work that we've done in the last 3 or 4 years with NWS and with Chris Coleman. So as I said, Merritt and Orton identified that there were tills at Drig and sea scale. Coleman said in 2021, Coleman et al. Suggested no tills at the Drigg Cliffs or at the LLWR. But subsequent work has identified tills have been identified at sea scale and similar units at Drigg, although the materials are generally less stiff. And tills now have been identified at the LLWR, maybe relating to the LGM. The ISIS, Nyrex and Merritt and Orton, they suggested the ISIS overrode Drigg and the LLWR during both ice re-advances. Coleman et al. Suggested that the ISIS didn't override Drigg and the LLWR. And we feel that the ISIS did not override Drigg and the LLWR during the last ice re-advance, assumed to be the Scottish re-advance, but has overridden the LLWR during previous events. And Merritt and Orton never considered an ice-dammed lake, whereas Coleman et al. Suggested an ice-dammed lake was present, which drained and refilled on multiple occasions. We feel that there was no ice-dammed lake, but there were ice proximal outwash plain environments, and this would have led to probably multiple proglacial lakes in the area. So hopefully what we've done is taken these two different approaches in the hypothesis, and we're coming up with a fairly unified approach, which does draw on both of them, but actually what it really does is demonstrate the quality of work undertaken by Sinead. So finally, I would just like to thank a few people that have helped us out. Obviously, Chris Coleman and his colleagues at Jacobs. Chris, you've seen me mention the Coleman et al. Paper on several occasions, and Chris has been fundamental in this research and has also allowed Sinead to develop her own ideas, even if they were slightly different to his. We've worked very closely, as I said, this is applied research, so we've worked very closely with a number of colleagues at Jacobs, such as Amber Pavey and Stephen Eaton. And obviously we've also been working with colleagues at NWS, and our thanks for the funding and the insight must go to John Shevelin as well. And here you can see when we all got together for a QRA meeting in West Cumbria, which was a fantastic weekend with the occasional heated debate. And our thanks must also go out during this meeting to John Merritt for his insights as well. So thank you very much, and here are a series of references.